Hello, everyone, and thank you very much to Fairlie and her colleagues for organizing this seminar. I very much support the comments by Dr. Stranell about the need for the nuclear industry to promote tritium as being safe right around the world. That's paramount, and it's probably the main reasons why at Japan, they're proposing to dump radioactive water into the sea. In other words, they have to keep up with the pretense that tritium is safe. I'm going to talk today very briefly about tritium and its dangers. Radiation and radioactivity is a very difficult matter to get across. I've spent 30 years of my life studying it, but at the very least, this will be an introduction to the dangers of tritium. And I'm also going to be showing you the link to my further work on tritium, which people can peruse at their leisure. Right. The first thing I want to get across is that there are broadly speaking, two kinds of radiation. Firstly, external radiation, the kind of radiation you get if you, say, break your arm and you go to the hospital and get an X-ray. But more serious is the radiation that you get from radionuclides inside your body. That is much more serious because it radiates you 24 hours a day, 365 days a year. And tritium is primarily and totally an internal radionuclide. So we really have to concern ourselves with internal radiation. Now, tritium is what we call a radioactive isotope. By that I mean, if you take a radioactive atom, it's unstable, it will disintegrate or decay with a given half-life. And when it decays, it releases energy and also oftentimes a particle. The two of them combined is called radiation. So that's what happens when we are irradiated from inside. These radioactive atoms stay in our body and emit radiation and particles inside us. So what is tritium? Well, tritium is the radioactive isotope of hydrogen, which is the smallest element. It has quite a long half-life, 12.3 years, and it decays by emitting a beta particle inside you. Here is a tritium atom. It has a proton and two neutrons, and it's a single electron going around about it. Why is tritium important? Well, it's for about many reasons. For a start, it's the vital component in nuclear weapons. When we talk about hydrogen bombs, that's the hydrogen. It should really be called tritium bombs. Tritium is produced in all nuclear reactors and reprocessing plants. It's produced in all disused reactors around the world. And it would be produced in fusion reactors if they ever got going. I doubt very much that would occur. What is the most common way of us seeing tritium is with radioactive water, tritiated water. We all know that water is H2O, like this. And one of these two hydrogen atoms is radioactive. So the water becomes radioactive. It's not something in the water, but it's the water itself. Here's a schematic diagram of water, two H's, and an oxygen atom at a 180-degree angle here. Now, one of these hydrogen atoms becomes radioactive. That's what tritiated water means. Now, one of the main phenomena of tritium is that it swaps with its radioactive atoms with atoms nearby. For example, this is a diagram of a number of water molecules, I beg your pardon. H is here, oxygen's here. And what happens is that, this has to do with quantum mechanics, is that these hydrogen atoms swap with adjacent water molecules like this. These two atoms will swap very quickly. And it takes about 10 to the minus 15 seconds. So that no matter where you've got tritium, you'll see that it spreads very rapidly throughout the environmental materials. It means that the tritium spreads very, very quickly, no matter where it's found. And that makes it dangerous. I'm going to talk now, switch to the various so-called safety levels of tritium in water. This is expressed in becquerels per liter. A becquerel is 1 nuclear disintegration per second. The EU has got a limit of 100 becquerels per liter. The United States is 7 times greater. In Ontario, where there's a lot of tritium because of the nuclear power plants, it has recommended a limit of 20 becquerels per liter. In Colorado, in the States, it's 18. In California, 15. These are recommendations, by the way. There's quite a lot of politics involved in these limits. For example, the Ontario government refuses to recognize what has been recommended. This limit here is just a recommendation, but it's not enforced by the Ontario government. Now, what I'm going to do now is show you some of the science behind the dangers of tritium. This is a map of, as it happens, the Danube River going through Romania. It doesn't really matter. This is a power station here, Chernivtsi. And this is the results of modeling of the release of tritium in a northwesterly direction over a 24-hour period. Shows you here what the doses are from ingestion. You can see that the closer you live to the power station, the higher the dose. And the reason why I'm showing you this is a scientific exercise by nuclear scientists, as it happens. Here we go here, the IAEA, back in 2007. And we could look at another study, for example, this one here, showing similarly, this is organically bound tritium doses after a release of 1 terabecquerel tritium from the Chernobyl plant. And so not Chernobyl, Chernivtsi plant. And so these are estimates of the radioactive isotopes coming out and the resulting doses, okay? So this may not be made available to the public, but this is what scientists actually do and what they actually figure out what will be the resulting doses. This is a chart showing that as the further away, the closer you get, I should say, to a nuclear generating station in kilometers, 40, 30, 20, 10, 0. These are the results of the concentration of tritium in air. As you can see, the closer you get, the higher the air concentrations. These are power stations in Canada. You may say, well, why am I using this? Well, because this is the only data that we've got available, which I can show you in an easily demonstrable form. This is air concentrations, but if you look at concentrations in soil, vegetation, and food moisture, you can see the same pattern. distance from the nuclear generating stations in kilometers. 100 kilometers, 10, 1, this is a logarithmic scale. You can see that it's more or less a straight line. And in other words, the closer you get to a nuclear facility, the higher the concentrations, and whether it's soil, vegetation, or milk and vegetables. So how do people who are living near nuclear facilities, and this includes Fukushima, get their tritium? Well, from water and food, water and drinks, breathing it in, skin absorption, and from organically bound tritium in food. In other words, people who live near nuclear facilities become tritiated. There's nothing you can do about it. You live there, you get tritiated. So that's why it's a danger, and that's why we are very concerned about TEPCO's and the Japanese government's proposals to dump tritium into the sea. Now, this is difficult for us perhaps to grasp. You can't hear it, see it, smell it, tritium. Oh, sorry, I'll go back one. But it's still there. We have to act as if it's present. And I'm going to give an example of this. For example, most of us do our cooking. We all know that when it comes to raw meat and raw fish, we're very careful, very wary about handling them because of the dangers of food bacteria. Even though we can't see the bacteria, we know that it might be there. So the same with tritium, we need to be wary and act if it's there, as if it were there. Okay? Now, there are serious problems about tritium. Why do I go on and witter on about tritium? The first is that it's quick distribution. Because of its extreme exchangeability of water molecules, and because that means that water is, of course, the most important element, item in the environment. It means that when you pump out tritium to the environment, it goes all the way through the environment very rapidly. In other words, as soon as you have tritium in the environment, the whole environment becomes contaminated. So it's a quick distribution. That's the first pattern. The second is tritium's radiation biology. It's got a very short-range beta particle, roughly speaking about the diameter of a chromosome. So whether it's dangerous or not depends where it is. For example, is it near DNA or RNA? If it is, it's very dangerous. In the past, particularly with the nuclear industry, they described tritium as a weak emitter. But if you know anything about radiation biology, is that the lower the range, the more dangerous it is. In other words, tritium has got a low energy, but it's got is more dangerous than those radionuclides which are strong emitters. Sounds paradoxical, but it's true. I'm a radiation biologist, so I know that to be the case. The third thing is its property of organic bounding. There's very little recognition given in whether by the nuclear industry or even by the IAEA or ICRP to the dangers of organically bound tritium. Essentially, when we get it inside us, it sticks to us and has a long half-life, or a long, not only long radiological half-life, but biological half-life. And this is very poorly recognized in the doses and what they estimate for tritium. So the overall conclusion is that official dose estimates for tritium are significantly underestimated. In other words, whenever we see them saying there's so many microsieverts, that's very unreliable. A good way of looking at it is to say it's the same as arguing that the number of angels on a pinhead. This is what religious arguments were in the Middle Ages. they argued, how many angels can you get in a pinhead? It's irrelevant and highly, and so these dose estimates for tritium are very unreliable. Now, it's not just me who's saying these things. This is 5 publications which are brought out, which show and discuss the controversy over tritium. This is the UK government report here, 2007. This is the IAEA report, again, 2007. My own report, United States report, and a good report by Arjun Makhijani. And you can dig these out and read them, and they say exactly what I've been saying. So the main conclusions that near reactors or all nuclear facilities, including Fukushima, there are high concentrations in the air, in food and water. That means high tritium exposures to people living nearby, and that means there's likely to be increased incidences of cancers, particularly leukemias and birth defects. But of course, you can't really pick these up unless you do really expensive and long-lasting epidemiological studies. And these are very few of them, and the nuclear industry tends not to conduct these studies. My recommendations are we should use the precautionary principle. In other words, we should err on the side of caution. Be careful. Secondly, we should do the epidemiology studies that I'm recommending. Thirdly, we should revisit tritium dosimetry and take into account all these characteristics which are dangerous. And most important, we should advise local people all about tritium's dangers. This is a link to my own website, which discusses the hazards of tritium. This report is about 14 pages long. I'm not apologetic about that. The point is that tritium does have a lot of dangers, and we have to study them. Thanks very much for your attention. Thank you.